Okay, so let me start by reminding you that we have the mathematics colloquium today. The speaker is Matt Baker from UC Berkeley. He's speaking at 4 o'clock here. And his talk is about the interaction between tropical geometry and combinatorics. So there's something called the Riemann-Roch theorem in classical algebraic geometry of curves. And there was something called chip firing games in graphs, which actually turned out to be very closely related via this thing called tropical geometry. And so he will explain that, so I very much encourage you to go. So my plan for today is the following. So we've seen a lot of different Hopf algebras in the last few weeks, this is not a precise classification, but there are kind of two kinds. There were two big kinds of Hopf algebras that we considered. Ones were coming from like incidence Hopf algebras, and so that's where we saw posets, graphs, matroids, polytopes, these kinds of things. And then we have considered in the last few weeks these algebras of symmetric functions, non-commutative symmetric functions, symmetric functions and non-commutative variables, quasisymmetric functions, things like this. And so what I want to do today is talk about this second class of Hopf algebras, and show you how they are interrelated in very intricate and interesting ways. Okay? So maybe a topic for a name for today can be many Hopf algebras and how they're related. Okay. And maybe what I would like to do is to begin by just writing down a whole bunch of I want to write down 5 different Hopf algebras that we have considered recently, and just to remind ourselves of how they work, I want to write down some examples. So one very important one is SYM, the Hopf algebra of symmetric functions. Okay. And I'm not gonna, since there's 5 of them, I'm not gonna go through all the details of all of them. But maybe what I'll do is just write down a basis element for each one of these things, and that way we will remember what they look like. So for the Hopf algebra of symmetric functions, we saw that there were a couple of different ways of writing the elements down. One way was to write down monomial symmetric functions. And so maybe what I'll do is that for each one of these things, I'm going to write down an element of degree 5. And I didn't plan ahead which elements of degree 5 I'm going to choose, so maybe you guys can help me. So what is a monomial of symmetric function of degree 5? 311, for example. And so this is meant to be the sum over all I, j, and k of xi cubed, xj, xk. Xj to the 1, xk to the 1. And remember that actually because we don't want, we want that if we switch j and k, that is only counted once, so we actually want to stipulate that j is less than k. And so we just consider all the monomials of exponents 3, 1, 1. Okay? So this is an example of a monomial symmetric function. And so this is one way of writing down a basis. But we had a different way of writing a basis, which was in terms of, well, actually we have several different bases. And I just want to remind you of another basis that I have, which is the H basis. And so one of the elements of that basis is, for example, H32, which is by definition H3, H2. And remember that H3 is the sum of all different monomials of degree 3, and H2 is the sum of all different monomials of degree 2. Okay? And so these are examples of elements of SYM. Okay? So this is one of those Hopf algebras that I want to discuss. And actually, maybe it's worth writing down next to each one of them what are the kinds of combinatorial objects that index the bases. And in this case, the bases are indexed by partitions. Okay. Second, another one that I have is NSym. See, now I have to... So which is NSym and which is NC-SYM? Remember, they're different from each other. And they kind of relate to two different variants of what I wrote down here. So I have to remind myself. NSym generalizes this second point of view. So in NSym, we don't really consider expressions like this. We just consider these generators H, okay? And NSym as an algebra is just going to be generated by H1, H2, H3, etc. But now remember that the important thing is that the H's don't commute anymore, okay? And so what is an example of a basis element here? Let's say in the H basis. So can you tell me an element of degree 5 in NSym? Are you being shy? Are you being nervous that you're going to say something wrong? 4-1. So that's an example, H4-1. What does that mean? It means H4, H1. And there's no other meaning. There's no other meaning in terms of anything like this. It's just H4 times H1. The generator called H4, which has degree 4, times the generator H1, which has degree 1. Okay. What's another generator? What's another basis element? And the reason that I'm not writing this one down is that, for example, another one is H1, H4, or H1, 4. Okay. The thing is that here we always write in SYM we always write these in decreasing order. But here, H4-1 is different from H1-4 because H1 and H4 don't commute. Okay? And so an example of something of degree 5 is H1-4. Or another example is, for example, H1-3-1. And this just means H1 times H3 times H1. And there's no further meaning here. The generator of degree 1 times the one of degree 3 times the one of degree 1. And then we have these operations. The multiplication is free, and the co-multiplication, we wrote it down. Okay, so those are the elements of NSym. They're just products of these formal things, H.
Just remember, so the generators are all these homogeneous monomials to degree n. Just remember.
So the generators are just H1, H2, H3, etc. And the basis elements are just all the products like this. And so they're indexed by things like this, which is what we call compositions. So they're sequences of positive integers, which are not necessarily in decreasing order. Okay? So this is given by compositions. Okay? Okay, so that's another one, NSym. A third one and a third one is NC-SYM. And NC-SYM is where instead of saying that the h's don't commute, we say that the variables don't commute. So these are the symmetric functions and non-commuting variables. Okay. So what are the monomials here? Sorry, what are the basic monomial symmetric functions look like? Well, they can look like this, but they can also look like, for example, like this. The sum of, let's say, I different from j, different from k, and it can be something like xi, xj, xi, xk, xj. Okay? So again, they're just, I mean, this is an example of a monomial in variables that do not commute. And then I just let that vary over all the different indices I, j, and k. Do you remember what we call this guy? What we would call this guy? I mean, this we can no longer index in terms of a partition because we have to know who are the i's, who are the j's, who are the k's. 1, 3. 1, 3 is where I is. 2 and 5 is where j is, and then 4 is where k is. And so this is an example of a basis element of NC-SYM. Okay. And so what are the combinatorial gadgets here? They are things like this, which is what we called set partitions. So you see, one reason that I'm putting all of these in front of you guys is so that you can see how they're similar and how they're different. And part of this exercise is to remember what each one of these things means. So do you guys remember NC-SYM? Okay. Another one is QSYM. Okay. So these are the quasisymmetric functions. And now remember that we don't necessarily need to be completely symmetric. We just need to know that if some variables are in the same order, then with the same exponents, then they have to have the same coefficients. And so an example of a monomial of degree 5, of one of the basic things of degree 5 here would be, I don't know, something like sum, and now you specify what order the variables are in, and then you just choose some exponents for those variables. So maybe you say that xi is raised to the something, xj is raised to the something, and xk is raised to the something. And since we're doing everything of degree 5 here, we should just choose 3 numbers here that add up to 5. And this could be, I don't know, 2, 1, 2. Is this a symmetric function?
Is that n of 5?
2, 1, and 2, yeah. And is it symmetric, or is it not symmetric? So Steven says no, so why not? So the thing is that when all the monomials that appear here have to be the smallest variable squared, the middle variable to the 1, and the largest variable squared. Okay? You never have the smallest variable to the 1, the middle one squared, the biggest one squared. Which, if this was symmetric, you should be able to rearrange the variables however you want and see the same monomials. Okay? But you cannot do that here because it's always the middle monomial that has the smallest exponent. So that's why this is quasi-symmetric, but it is not symmetric. Okay? And we gave a name for this thing, and I think I called it capital M. And then I labeled it by the exponents. So what are the combinatorial gadgets here? Well, you see all I did is choose what the exponents here were. And these are just any positive integers, not necessarily decreasing. So again, this is given by compositions. Okay? So that is a fourth Hopf algebra that is related to these. And I know that I went through this one very quickly, so is it clear what a quasisymmetric function is? Do you guys have any questions about it? I'm going to say a little bit more about these. Now,
What is the inclusion, if there is any? There's no inclusion? Well, I guess in that sense, they aren't even labeled in the same way.
so it's a great question, right? It's a great question, and it's vague, and maybe that's intentional. What is the inclusion? So there's actually 12 different inclusions that I could have here, right? There's 12 ordered pairs, and so do I have an inclusion? One inclusion is that if you're symmetric, you're quasisymmetric. So that's one inclusion. If you're And so basically, the point of today's class is to settle exactly that. Okay, so I'm gonna show you a lot of different Hopf algebras, and I'm gonna show you all kinds of arrows between them: inclusions, surjections, projections, blah blah blah, quotients. You're gonna like the class today, Brian. we're gonna have quotients, all kinds of things. Okay. So I'll have a much better answer to that question as we go on. Okay. I want to bring up another Hopf algebra that I believe, actually saw the first day of class, and we haven't seen in a while. And I'm going to give it a different name so here's a name that I haven't used, and I hate this letter, but this is what people use. And I actually don't even know I forget how to write this in LaTeX. Does anybody know? Is it frac S? I think. So that's meant to be something like an S. Okay. Frac S-SYM. And if you've seen this letter before, often you encounter it in combinatorics. Sometimes people call the symmetric group SN, except that they use this funny S. Okay. And here the labeling objects are permutations. That's why we call it frac S. SYM. Okay. What is the Hopf algebra permutations that we saw? Do you guys remember? This is a little bit of ancient history, but we saw Hopf algebra permutations where you started with a permutation, and the coproduct was cutting the permutation in two, and then standardizing each piece, and the product was taking two permutations and shuffling them in every possible way. So this was our shuffling cards Hopf algebra. Okay. So what is an element of degree 5 in this Hopf algebra of permutations? A basis element. Well, here the basis elements are the permutations. Okay. And sometimes we write them just by the permutation, but maybe it'll be a little bit clearer if I call it F sub a permutation. And so, I don't know. Tell me a permutation of 1 up to 5. Carla. Any permutation will do. Just so you know that I'm not making any special choices here. We didn't plan ahead of time which one she was going to choose. Any permutation of 1 up to 5 is one of the basis elements of the degree 5 piece. Okay. And this doesn't mean anything else. I mean, this is just that's the name of the element, and it's not equal to anything. It's just that's what it's called, and it's some formal variable associated to that permutation. Okay. So these are 5 different Hopf algebras, and my goal for today is just to show you that these are intertwined in really interesting and intricate ways. Okay. Okay. So maybe before I do that, I want to say, okay, so maybe I'll say something quick about 4 and 5, because 4 we saw a little bit too quickly, and 5 we haven't seen in a while. So some comments on 4 and 5. So let me make 2 comments about this. So recall that we have a bijection subsets, or between the compositions of n compositions of a number n and the subsets of the numbers from 1 up to n minus 1. And the way this works, maybe this is clearest in an example. Let's say that n, so this is for each fixed n, okay? So let's say that n is equal to 9, okay? So, okay. I don't know why I'm starting to do this, maybe when there's only 3 classes left, but I'm cold calling today. So I'm going to ask somebody to give me a composition of 9. So Lisa, give me a composition of 9. Some way of writing numbers that add up to 9.
1 and 8.
1 and 8. Why don't you give me a longer one?
Okay,
that one is fine too, but
2, 2, 2, 1.
2, 2, 2, 1. Now, just to remember that it's a composition and not a partition, I'm just going to juggle your elements around. Okay? So let's say that I do 2, 2, 1, wait, 2, 2, 2, 1, 2. So those elements add up to 9, right? And so then from this, I need to make a subset of n minus 1, okay? And so a subset of the numbers from 1 up to 8. And so I do this by taking the partial sums. So I take the first one, 2, then the sum of the first 2. 2 plus 2 is 4. Then 2 plus 2 plus 2 is 6. 2 plus 2 plus 2 plus 1 is 7. And you see, I could write 2 plus 2 plus 2 plus 1 plus 2 is 9. But if I were to write this, then every single composition would have that number 9. And so I don't really need to write that down because I already know that n is equal to 9. It also doesn't fit in the numbers from 1 up to 8. But that's why the bijection goes only up to 8. Because the number 9 would always appear, and so that's why we don't write it down. Okay? So we have this bijection. And it is a bijection because if I cover up this guy, you can tell me what the composition was, right? You just take the differences. First 2, then between here and here I need a 2. Between here and here I need a 2. Between here and here a 1. And between 7 and 9 I need a 2. So this is a bijection. And that means that I'm going to allow myself to write instead of writing, let's see, budgeting my board here. Instead of writing m 2, 2, 1, 2, I can allow myself to write m of 2, 4, 6, 7 in QSYM sub 9. Okay. So in the degree 9 things, instead of using the composition, I can use the set. And because there's a bijection between these, I can do this. So that's going to be useful sometimes. Now, the other thing that I want to discuss is a second basis so the fundamental quasisymmetric function f sub some composition is going to be equal to the sum over all the different, or maybe sometimes it's customary to write compositions by Greek letters, lowercase Greek letters. So like this, where this order is the order that we discussed, which is refinement. Okay? And yeah, so this order is refinement. So f of a composition is equal to m of that composition plus m of all the refinements of the composition. Okay. Now, what is a refinement of this composition? It's chopping up the pieces further. When you refine it, you make it finer. Okay. So if this piece is 2, you could either leave it as a 2 or write 1 plus 1. Okay. Okay. And one thing that is pretty easy to see is that these are also a basis. And the reason for that is that each f alpha is equal to m alpha plus smaller things, which means that when you write the transition matrix, it's going to be upper triangular, because every term is equal to the term in the corresponding row plus ones from either earlier or later rows according to how you did it. Okay? But this matrix is clearly upper triangular, and therefore these guys are also a basis. Okay? And so this gives me a different basis that I can use that is useful. Okay? Okay. So that's one thing that I wanted to mention, and then what I wanted to mention about S-SYM is just to remind you real quick how we multiply here. So, and co-multiply, so delta of F 2, 1, 3. So this is a, so we take this this permutation, and we cut it up in every possible way. So you either cut it at the beginning, and you get this, plus, now you could cut it at 2 and then 1, 3, right? So I kind of want to write F2 and F1, 3, except that I cannot do that, because the indices here always have to be the permutations of the numbers from 1 up to n. And so instead of writing F2, I have to standardize and write F1. And instead of writing 1, 3, I know that I have 2 elements, and this one is smaller than this one, so standardization is 1, 2. When I cut here, the left is F2, 1, and the right is, the standardization is F1. And when I cut on the right, I get F2, 1, 3 tensor 1. So that's the coproduct. And I also wanted to remind you how the product goes. So let's say that I multiply F1, 2 times F2, 1. So the way this works is that I shuffle So I think that these are the numbers 1 and 2. Now these ones become the numbers 4 and 3, and I shuffle these in every possible way. So F1, 2, 4, 3 plus F1, 4, 2, 3 plus F1, 4, 3, 2 plus F4, 1. Let me know if I make a mistake. Plus F of 4, 1, 3, 2 plus F of 4, 3, 1, 2. Okay, so these are all the different ways of shuffling 1, 2, 3, and 4. According to, sorry, these are the ways of shuffling on my left side, on my left hand, the cards 1 and 2 in this order, and on my right hand, the cards 4 and 3 in this order.
And then you're standardizing the second combinatoric?
Right, so I take my left cards to be the cards 1 up to k, and then these guys become the cards k plus 1 up to n. Okay, so this is a reminder of how this works. And now, let's go for the arrows. So I'm going to show you that there's all kinds of arrows here. Actually, let me make a couple of comments about this, though. Maybe I'll just mention them, but not write them. So one point that I want to convey to you is that this is all fairly recent work, and much of what I would like to say today is actually open. So some of these things are recent, some of these things are not understood. But for example, two very recent theorems from the last 10 or 15 years is that both QSYM and S-SYM are free. They're free as algebras. So you have a number of generators which generate them freely. Okay, so we knew that, for example, for SYM, it's a non-trivial theorem that the H's are a nice choice of elements that freely generate SYM. And it turns out this is that here you can be intelligent about what quasisymmetric functions you choose so that they generate all of them in a free way. And you can be intelligent about what elements of S-SYM you choose so that they generate in a free way. Okay? That's one thing. The other thing that I think is pretty interesting, and this is a theorem that I think it's more of an observation, but I think this is not 10 years old, is the observation that here, so first of all, there's a formula for the antipode that is very recent. But one thing that is surprising is that the antipode of this guy has infinite order, which is the first example that is not, I mean, usually all the antipodes that we see are of order 2, unless we kind of cook them up to be weird. But this is a very natural Hopf algebra that is indexed by very natural combinatorial objects, and here the antipode has infinite order. And that's something that was noticed pretty recently. And I wrote down some references on the notes that you can look up. But I thought maybe that would be interesting to some of you guys. But then what I'm going to do for the rest of today is focus. So we already talked about many Hopf algebras. So this 5 is many. And now we're going to focus on how they are related. Okay? Because they're related in many ways. So let me do this in 2 steps. First, let me relate Sym, NSym, and NC-SYM. So in class last time, someone suggested, I forget who, a map from Sym to NC-SYM. Actually, an inclusion from SYM to NC-SYM, given by taking a monomial symmetric function here, where the variables commute, and then just taking that formal expression and just, so maybe what I'll do is call the variables here x, okay? So I write down that expression, and I take that expression and I just rewrite it, except I write it in a new set of variables that is now not commutative. Okay? So commutative, the x's are commutative because they're in SYM, and in NC-SYM, so actually I'm going to switch to y's there also so that we remember that they're not commutative, okay? So this is non-commutative. So let me throughout use y to represent variables that are not commutative, and the x's are going to represent variables that are commutative. Okay. There's some issues here. For example, the thing is that a monomial like x1 cubed x2 actually can be written in different ways here. You can write x1 cubed x2, you can write x2 x1 cubed, x1 x2 x1 x1, and because the variables commute, those things are all equal to each other. But when you go to map them here, they become different. And so I have to be a little bit more careful about how I define this. But you could say, for example, write the monomial in order from smaller to bigger. So write it, the smallest letter first, then the next one, and so on, like x1 cubed x2. And this is how we did it last time. So take the monomials, write them in alphabetical order, in lexicographic order, and just translate them into variables that don't commute. Okay? And we did this last time, and you guys fooled me into thinking that this was an algebra map, and I said that it looked like it was, but it turns out that this is not. I thought about it later. This is not. So this is a linear map, that's fine, but this is not an algebra map. And I'll leave this exercise for you. And I also wrote it down in the notes. I computed how, if I call this f, then f of m1, m1, m1 is not the same thing as f of m1, f of m1, f of m1. You write it down, and you'll see that here the variables commute, here they don't commute, and that means that these things are not equal to each other, because here you can commute them and here you cannot. Okay? So, okay, well that's maybe good, maybe bad, but this map is not really an algebra map, and therefore it's not a Hopf algebra map, and therefore it doesn't really belong in this class. We want Hopf algebra maps. Okay. Now, there's actually other maps. I would say that there's a more natural map, which is to do the same thing but backwards. Because you can start with some expression where the variables don't commute, and then just forget that the variables don't commute. Okay? And so that actually is a map. So we do have a map. And it's actually the exact same map, but the other way around.
Is it fair to say then the NC-SYM descends to SYM as an algebra?
So this is, well, let me address that in a second. Let me first write down what the map is. So the map is forget that you don't commute. That's the name of the map. So for example, I take this generator, M1, 3, 2, 5, 4. Where does that go? And another thing that you should notice is that I meant to do. I'm going to try to remember that non-commutative things I'm going to write in bold, like this guy, because it lives in NC-SYM. I'm going to write it in bold. So when you forget that the variables don't commute, what thing do you get? These things.
Each partition collapses.
You get the sum of xi squared, xj squared, xk. The sum of xi squared, xj squared, xk over I different from j different from k. Is it symmetric? Yeah. Okay. And this, it's very straightforward to check that this actually is a Hopf algebra map. Okay. Now, Stephen's question is, does that mean that the algebra structure here descends to the algebra structure here? Well, it might mean that if this map is surjective. So, is this map surjective? Well, one thing that you might ask is, given any monomial, so by the way, what is this in monomial notation? M2 to 1, is it right? This is almost right, except that I and j, when you switch I and j, that appears twice. Here you were adding over all the different I and j, and so we get yi, yj, yi, yj, and we also get yj, yi, yj, yi, which means that actually terms appear twice. Okay. Because M2 to 1 would force I to be different from j, like we did here. In M311, we force j and k to actually be j to be smaller than k. And if you don't force that, then you get twice as many terms. Okay? But you basically get some constant times the monomial symmetric function. And so I would argue that this is surjective. Why is it surjective? Because no matter what thing you want to get here, you can easily cook up a partition that maps to it. Right? And so actually, this is surjective. So this map is surjective. So this, I want to say this Hopf algebra map because I want to emphasize that this really preserves the whole structure of the Hopf algebra. It's surjective. And so this means that NC-SYM projects onto SYM, okay? Which kind of makes sense. Okay, so now, okay, so is that clear what this map does? This map just forgets that the y's don't commute. Okay, so given this, can you tell me another similar map that we have between Sym, NSym, and NC-SYM? We just wrote down a map from NC-SYM to Sym, which forgets that the y's don't commute. So what can I do between Sym and NSym? I can do the same thing, except that I can now forget that the h's here don't commute. And here, again, I meant to write these as bold h's because even though it's customary to use the same letter, it's a little bit unfortunate because they represent different things. And so let's make bold h's be the ones that don't commute, and non-bold are the ones that commute. And then I can write a similar map from here to here that just forgets that the h's don't commute. Okay. So we also have a different map, which I'm going to call psi, from NSym to Sym. which takes the non-commutative HI, the non-commutative version of HI, and sends it to the commutative version. And again, this map is just forget that the H's don't commute. The both H's don't commute. Okay? Yeah?
I love how you also forget the last quotation, the second quotation.
I don't love it.
Well, it's just going along with the theme of forgetting.
Thank you. Okay. Is this surjective? Well, we know that these guys generate SYM, and for each one of these we have a preimage. So that means that this is surjective. By the way, this is something that drove me crazy when I was taking algebra. The professor always wrote these arrows and never explained what they were. And this double arrow means surjective. Okay? So when I say surjective and I write the extra arrow, let me explicitly say that to you, that this arrow means that the map is surjective. Okay? Okay. So what does that say? Is anybody a subalgebra, a quotient, anything? If you remember, we have the first isomorphism theorem, which if we apply it to this, tells it that because this map is surjective, I mean, the isomorphism theorem says image is this mod kernel, they're isomorphic. The image is SYM, so it says that SYM is isomorphic to NC-SYM mod the kernel. Okay? And so this says that SYM is a quotient of NC-SYM. And similarly, it's a quotient of NSym. Okay? So let me write this down. So SYM is a quotient of NSym and of NC-SYM. Okay. So this tells us that how SYM is related to either of these two things. But that leaves the question, since I'm trying to relate three different things, the question is how are the other two related? Do you have a sense of which one is bigger or smaller, or is there can we make sense of that? Between NSym and NC-SYM. So here we forgot that the variables commuted, and here we forgot that the H is commuted. We did two different things. So are these two related in some way, or are they just kind of orthogonal constructions that have nothing to do with each other?
I think NC-SYM is above NSym is above SYM.
Okay, so let's see about that.
If you keep like the y's in NC-SYM and like keep them attached to the H, and then you say all those H's don't commute anymore, we'll have the structural reason why.
So let me articulate a reason for why these two are actually also very closely related. So I'm gonna construct a map from NSym to NC-SYM. Okay? So the map chi has a pullback, okay, from SYM to NC-SYM, which is not the one that we wanted to write over there. Okay, so the point is we wrote the wrong map. but there is a correct map that we could have written. What do you think the correct thing is to write if that failed? We took a commutative monomial symmetric function, and we tried writing down the same thing, but except that things don't commute now. So what I'm going to do, the thing is that I took something like xi squared xj, and I tried to map it to yi squared yj. But that means that I favored yi squared yj over all the other non-commutative versions of that, like yi yj yi or yj yi squared, and there's no reason why I needed to favor that one. And what I'm going to do is not favor it. I'm just going to consider them all. Okay? So what I'm going to do is I'm going to say that, let me first write it in an example, and then, so what I'm saying is that if I wanted to make a non-commutative version of this, then actually I should be considering this is one possible non-commutative version, but there were two others that I should have also considered. And so that's what I'm going to do. What I'm going to do is that I'm going to map this to all its non-commutative variants. And let me write here, I sum m sub pi of y over all the different set partitions, which would give me lambda. Okay? And I could write down blah, blah, blah what this means, but really what this means is this. Just look at all the different, instead of writing a formal definition, let me just say, I'm mapping this to all these possible non-commutative versions. If you were to, okay, so that's the pullback, and so the point is that okay, so what does it mean to be a pullback? It means that the composition of these two maps is the identity. Now, I think this is almost true, but not exactly true, and I think one of my definitions must be slightly off, and let me explain why. The issue is this 2 that we had right here. There's always the question of whether you keep track of these multiplicities or not. Okay? Now, the thing is that if you apply my map chi to this, you're not going to get this, right? Because this gives you this gives you this, and this gives you this. And so actually, chi of chi star of this is 3 times the identity. It's not the identity. And so that means that I'm off by a constant. And so I'm just going to ask you to trust me that it's just a small mistake that I made, but this can be fixed. Okay? And to be honest, I don't know exactly where the mistake is, but we're off by a constant somewhere, and that can be fixed. Yeah?
Do you think the multiplicities might mean anything?
Yeah, the multiplicities absolutely mean something, and you can actually compute them. That's another exercise that is not too hard. What is the multiplicity? This is a number that, if I give you this, if I give you this partition, you can tell me what the multiplicities are. And yeah. So let me write here modulo some small mistake that I'm making. The thing about all of this is that every one thing that I'm telling you comes from a different paper, and every paper uses a different convention. And I was worried this was going to happen, and I'm sure it's not the only time it's going to happen in today's class. Okay? Every single arrow comes from a different paper, and there are ways of making all these conventions together, but there might be some small mistakes. Okay, so what's the point? The point is that this gives me a map. By the way, because that was a surjection, this is going to be an inclusion, and that's what this little thing means. This is an inclusion. Okay. And so I'm going to get an inclusion of NSym into NC-SYM. And what this inclusion does is that it first goes to SYM and then goes to NC-SYM. What maps do I use here? Well, to go from here to here, I use psi, and to go from here to here, I use chi bar. Okay? And this is my inclusion I. And so this shows concretely that NSym is actually a sub-algebra of NC-SYM. It really lives inside there. It's smaller, and it actually lives inside there. Okay? And so this is how some of these, how these guys are related. Yeah?
Was that not obvious before that it lives inside NC-SYM? Because I didn't think it was.
I didn't think it was obvious, no. I still don't think it's obvious. Okay. Let me summarize this into the following diagram. For those of you that like commutative diagrams. I'll summarize the situation. So here's the inclusion. Here I have my projection onto SYM. Here I have my projection onto SYM. And actually these guys are just equal to each other. So this is just the identity map. Okay. So this summarizes the relations between these three algebras. Okay. So that's the first part of the story.
The down arrow on the left, the restriction of the down arrow on the looking mirror is your commutative diagram.
Yeah,
The
so
down arrow on the left is the restriction of the arrow on the right to NSym.
So this is, if you're looking at that picture over there, this is I, this is psi, this is chi, and then there's an arrow here which is chi bar, chi 12.
NSym lives inside NC-SYM.
Mhm.
You should not be able to restrict the map from NC-SYM to just the elements of NSym.
And that's what this is saying. This is saying that if you project, you get the same thing as if you regard it as an element of NSym and then project. So it's exactly what you're saying. That these projections are compatible with each other with respect to this inclusion. This is a diagram you can stare at for a while, and I really recommend it. But I want to get to how the other guys are related. I want to relate now Sym, NSym, QSYM, and S-SYM. let's talk about how these guys are related. Now, I already have a map from NSym to SYM. So I have a projection of NSym onto SYM, which just forgets that, that you're commutative. Okay? There's another simple map that I have, which is the one that Stephen mentioned earlier. I also have that everything symmetric is quasisymmetric. If you're a symmetric function, then you're clearly also quasisymmetric. Okay? Okay. Now, here there's already something interesting. Because if you remember, we have this notion of duality of Hopf algebras, where we showed that SYM is self-dual. Everything I'm going to say is about graded duals. All of today, whenever I say dual, I mean graded dual. We showed that SYM is its own graded dual. And I outlined to you last time that these guys are dual to each other. NSym and QSYM are dual to each other. Okay? So the thing is that this is... The point is, whenever you have a map from A to B, you have a dual map from B star to A star. And what I'm saying is that here I have a map from A to B, which gives me a dual map from B star to A star. And these are actually dual maps to each other. They're not just, I mean, we kind of reach them separately, but they actually are dual maps to each other. So, and these are dual maps, which is a non-trivial statement. Okay. So I have this map, I have this map, and they're dual to each other. And so that's, I would say, how these three are related. You know, I have SYM, NSym projects to it, SYM goes into QSYM, and QSYM and NSym are dual to each other. Maybe I'll actually draw what I'm saying so that you can look at it. So NSym projects onto SYM. SYM lives inside QSYM. And there is an arrow here of duality, which I'm not going to draw. These guys are duals. When you project, you always become smaller. So this guy is bigger than this guy. This guy is included into this guy, and then these guys are the same size because they're dual to each other. So SYM is a quotient of one thing and an inclusion of the dual. Okay. But I haven't brought in S-SYM into the picture, and I should do that. So I'm going to do that now. I'm going to relate S-SYM and QSYM by giving a map between them. So what I'm going to do is the following. It's so hard to draw. So how am I going to relate S-SYM and QSYM? What I'm going to do is this is if we go back to here, S-SYM needs to go to QSYM. So combinatorially, we're thinking that permutations need to go to compositions. And by the way, because of that bijection between compositions and subsets, we might also think here that when we have compositions, we also have subsets. I mean, they're kind of the same thing. So to go from S-SYM to QSYM, I need to find a way of relating permutations and sets. So there's going to be some combinatorics involved. And what I'm going to do is that given a permutation, I'm going to define a set. And let me ask you, actually, I'm going to give you a permutation. Here's a permutation. 7, 2, actually, no, I'm cold calling today, so who haven't I asked? Krista, give me a permutation of the numbers from 1 up to 7, and one that is not too boring. Anything. Just don't give me the identity. 2, 5, 3, 4, 1, 7, 6. That's a permutation. Now, we need to make a set out of it. So there's different things you could do. So think about it. Given a permutation, I want to define the set, a set corresponding to it. And it should be a subset of the numbers from 1 up to n. To n minus 1, actually, right? Because remember that we don't have the subsets up to n, we have the subset up to n minus 1. So what subset of the numbers from 1 up to 6 would you associate to this? Different choices. Does anybody have any ideas? I'm being very, very vague. I'm just saying, I'm giving a permutation, give me a set. And you should need to look at the permutation to figure out what the set is. I'm being totally vague.
Well, take the things to the left of the 7, put them together, and the thing on the right of the 7, and that's the 2 elements of the 7.
Okay. So that's one thing you could do.
Well, look at the elements in the permutation and turn them into singletons.
So just drop the 7 and then. So for example, I don't want to just say drop the 7 and consider everything because I'm going to get always the same set. The set should say something on the permutation. One point that I want to make to you is that there's many possible choices here. Okay, and one thing that you could do is what's called the descent set, which is where this permutation descends when it goes down. So when does it go down? It doesn't go down from 2 to 5. It goes down from 5 to 3. It doesn't go down here. It goes down here. It doesn't go down. It goes down. So I'm going to say that the descent set, this is what? So does it work if I say 5, 4, 7? It doesn't because I want a subset from 1 up to 6. And so then, I mean, that you might have tried that, but turns out this doesn't work. So I could do just 5, 4, but then I would be forgetting this, and I want to pay more attention to the permutation. Again, there's different choices. What I'm going to do is just see what positions this happened in. This happened in positions 2, 4, and 6. And the point is that you can never have a descent in the last position because you have nobody after it. This is at this point, this is very arbitrary, but I'm going to do it anyway. These are the elements such that ui is bigger than ui plus 1. You could do the same for ascents. I do it for descents. Crazy thing is that this is a Hopf algebra map. So here's a proposition. If I take SYM and I map it to QSYM by taking a generator here is given by a permutation. What is a generator here? Well, I just erased it, but QSYM has 2 different bases, the M basis and the F basis. And turns out that if you choose the F basis, the descent of U, this is a Hopf algebra map. It's a really beautiful observation of Claudia Malvenuto, By the way, I should say, if I haven't already, that S-SYM is often called the Malvenuto Reutenauer Hopf algebra of permutations. So this was in her PhD thesis under his direction, and then they wrote a couple of papers together. Okay. And so she proved that this is a Hopf algebra map. Really beautiful. So it says that if you do product here, that corresponds to the product here, which is very non-trivial. But I mean, you can give a proof. This would have been a good homework problem if we still had serious homework problems that were not just computations. Okay, it's a Hopf algebra map. Okay, now is it injective? Is it surjective? So can you have two permutations with the same descent set? Yeah, right? For example, if I switch 1 and 2, that would still be the same descent set. That means that this is not injective. You can have two different U's that go to the same descent set. It's a surjective. If I give you positions for the descents, can you invent a permutation that descends precisely there? Yeah, probably, right? You can do it. I know you can do it. I mean, if I tell you, give me a permutation that descends in positions 2, 5, and 7, and I give you a minute, you will do it. And if I tell you to give me a general procedure, if I give you a few minutes, you will figure out how to do it. So this is a surjection, actually. Because these guys are a basis for QSYM, this is actually a surjection. Okay? So I have a map right there. Okay. I hope you're tempted to draw a map this way also. Hopefully we can find a map here. And I do have a map, which is actually an inclusion, I believe. Yes. Oh, from NSym to S-SYM, sorry. What is this going to do? What is a generator of NSym? Something like H131. Which I want to write in set notation. So what is this in set notation? Nina, it's your turn. So I want the set that corresponds to this composition. So now it's what the partial sums are. So to go from a composition to a set, you tell me what the partial sums are. So does that make sense? So anybody want to tell me what the set corresponding to this composition is? It's 1, then 1 plus 3 is 4, and then 1 plus 3 plus 1 is 5, but I don't write that one. I know I confused you because in the previous one we were doing something different. I'm going to take H14, and I'm going to map this to the sum of all the permutations whose descent set is 1, 4. And I claim that this is a Hopf algebra map. This is a Hopf algebra map. Again, it's another non-trivial statement. And it tells me that this is a Hopf algebra map. Okay? And so I have this relation between them. Okay? And this is, if you go to combinatorics conferences and people talk about combinatorial Hopf algebras, this is a diagram that you keep seeing over and over again, because these are four very important fundamental Hopf algebras, and they're related to each other like this.
Now we need NC-SYM to S-SYM, because NSYM lives inside both of them.
So give me a second, because I want to say more about, before trying to combine these two, which Brian would do, and I'm happy for that. I want to focus on this one because there's more that I can say about this. Because I said that these two are duals to each other, and this map is dual to this map. So what would be the ideal thing that you could say? That there's something dual about this one. And in fact, it turns out that this one is also self-dual, and this map and this one are dual maps. So if you take the dual of this picture, it just flips it like this. And there's, duality, these two are self-dual, and these two get swapped. And so let me write some facts also. This guy is self-dual. And these two maps, and these two last maps are dual. Okay? So another really beautiful relation between these guys. Okay. What would Brian do? How do we fit all these things into one? We have this diagram, which I want to overlay with the other one. And I'm going to do it like this. What do you want to do, Brian? What is it?
I want to know about NC-SYM and S-SYM.
You want to know about NC-SYM and S-SYM.